The day the edge stood still. Analyzing the Cloudflare November 18th, 2025 outage. Hello everyone, and welcome back to the channel. If you were online on November 18th, 2025, you noticed the silence. It wasn't the silence of a disconnected cable or a local power outage. It was the eerie, digital silence of 502 bad gateway errors cascading across nearly 20% of the visible web. We are talking, of course, about the major Cloudflare outage that took place earlier this week. For about 83 minutes, the Internet's immune system caught a fever. Dashboards froze, API keys stopped validating, and for thousands of businesses, the edge became a cliff. Cloudflare has just released their official postmortem on the blog, and it is a masterclass in distributed systems complexity. Today, we aren't just reading the news, we are tearing apart the architecture. We are going to look at the difference between the control plane and the data plane. We're going to discuss the thundering herd problem in distributed databases, and we are going to analyze exactly how a routine software update turned into a global blackout. If you are a back-end engineer, a DevOps specialist, or a CTO, you need to understand this failure because it highlights the fragile balance between consistency and availability in global networks. Let's dive in. The timeline, from routine to red alert. To understand the engineering failure, we first need to establish the sequence of events. This wasn't a malicious attack. It wasn't a DDoS that overwhelmed the pipes. It was, as is almost always the case in high-severity incidents, a self-inflicted wound born from maintenance. According to the incident report, the trouble began at 1342 UTC. Cloudflare's engineering team initiated a scheduled migration of their core configuration management database. This is the system responsible for storing your DNS records, your WAF rules, and your worker scripts. They were moving from a legacy sharding strategy to a new dynamic partitioning scheme designed to handle higher write throughput. At 1345 UTC, the migration scripts began executing. The telemetry looked green. Latency was nominal. But at 1349 UTC, the first alarms fired. It wasn't the traffic serving layer that screamed, it was the API. Customers attempting to push new code to Cloudflare workers or update firewall rules started seeing timeouts. By 1400 UTC, the issue metastasized. It bled from the control plane, the API and dashboard, into the data plane, the actual traffic flow. Edge nodes in Frankfurt, Singapore, and Ashburn began failing health checks. They weren't crashing, but they were rejecting valid traffic because they couldn't verify customer configurations. At 1415 UTC, Cloudflare declared a P0 critical incident. So, what actually broke? To answer that, we have to look at the architecture of the edge. The architecture of failure Cloudflare, like most hyperscalers, relies on a strict separation of concerns: the control plane and the data plane. The data plane is the muscle. These are the thousands of servers and data centers around the world that process packets, terminate SSL/TLS, and cache content. They are designed to be incredibly fast and fail open. If they lose contact with headquarters, they are supposed to keep serving the last known good configuration. The control plane is the brain. This is where you log in. When you toggle a switch to under attack mode, the control plane writes that state to a database, which then propagates that change to the data plane across the globe. The November 18th outage was a catastrophic failure of the mechanism that bridges these two worlds. The consensus problem. The root cause traces back to a distributed consensus failure. Cloudflare uses a highly consistent distributed key-value store to manage global configuration. Let's call it core config. When the migration script ran, it was supposed to lock a small shard of the database, move the data, and unlock it. This is standard procedure. However, the postmortem reveals that a logic error in the retry mechanism of the migration script caused a lock storm. When a shard failed to migrate instantly due to minor network jitter, the script didn't back off exponentially. Instead, it retried immediately and aggressively. Worse, it didn't release the read locks on the adjacent shards. Within minutes, the database was deadlocked. Now, here is where it gets interesting for us system architects. Why did a database lock take down the edge? The dependency loop. Ideally, the data plane should function autonomously. If the database is down, the edge server should just keep serving the old rules. This is called static stability. However, Cloudflare revealed that a recent feature update regarding instant logs and real-time bot management had introduced a hard dependency. The edge nodes were configured to fetch a fresh session token from the control plane every 15 minutes to validate their ability to write logs. When the database locked up, the control plane couldn't issue these tokens. When the tokens expired, the edge nodes, following a strict security protocol, stopped processing traffic that required logging. Since almost all enterprise traffic requires logging, the edge nodes defaulted to a fail-close state to preserve data integrity. This is a classic architectural trade-off: availability versus consistency. Cloudflare security protocols prioritize consistency, ensuring logs are authorized, over availability, passing traffic blindly. On November 18th, that trade-off cost them 83 minutes of downtime. Resilience models in the cloud. This incident forces us to compare how different providers handle this specific class of failure. It's easy to point fingers, but this is a problem every major cloud provider faces. Let's look at how this compares to the architectural philosophies of AWS and Google Cloud. The regional versus global model. Cloudflare operates a global control plane. When you change a setting, it replicates worldwide. This provides an incredible user experience. Your changes are live everywhere in seconds. However, the blast radius of a global control plane failure is, by definition, global. Contrast this with AWS, Amazon Web Services. AWS is famously strictly regional. If US East 1 goes down, which, let's be honest, it does, your resources in EU Central 1 are theoretically untouched. Their control planes are sharded by region. The downside? You have to manage multi-region replication yourself. It's more work for you, but it limits the blast radius of a single bad update. Fail open versus fail closed. This outage highlighted the danger of fail closed defaults. In a fail open scenario, if a security service fails, the traffic is allowed through. The risk is that you might let a malicious packet in. In a fail closed scenario, if the security service fails, the traffic is dropped. The risk is you block legitimate users. For a security company like Cloudflare, the instinct is to fail closed. If the WAF, Web Application Firewall, can't check the rules, it shouldn't let the packet in. However, for general content delivery, you want fail open. If the cache can't verify the user, just serve the image anyway. The November 18 outage was exacerbated because the dependency on the logging token forced a fail-closed behavior on traffic that arguably should have been fail-open. This is a configuration nuance that I expect many engineering teams are reviewing this week. Cost of complexity. There is also a hidden cost comparison here. Cloudflare's architecture is designed to be serverless and abstracted. You don't manage the OS, you just run the code. This abstraction relies on complex orchestration layers. Comparing this to running your own Nginx fleet on bare metal, if you ran your own servers, a database lock in your control panel wouldn't stop Nginx from serving traffic. You lose the convenience of Cloudflare, but you gain the simplicity of isolation. This outage serves as a reminder that serverless really just means someone else's servers, and you inherit their architectural dependencies. Real-world scenarios, the impact on the ground. Let's move away from the abstract and talk about what this actually looked like for engineers on Tuesday. Scenario A, the e-commerce nightmare. Imagine you are the CTO of a mid-sized e-commerce platform. It's November. You are wrapping up for Black Friday. You have aggressive caching rules set up on Cloudflare to offload traffic from your origin servers. At 1400 UTC, your monitoring tools go red. But here is the kicker. Your internal health checks are passing. Your servers are up. The database is fine, but no traffic is coming in. You try to log into the Cloudflare dashboard to disable the WAF, thinking maybe a rule is misfiring. You can't log in. The dashboard returns a 500 error. You are locked out of the cockpit while the plane is diving. This is the control plane nightmare. You have no levers to pull. You are completely at the mercy of the vendor's recovery time. Scenario B, the CI/CD pipeline trap. Consider a SaaS company using Cloudflare workers to render their front end. They have a CI/CD pipeline that deploys a new version of the worker on every Git merge. At 1350 UTC, a developer merges a hotfix. The pipeline triggers the deployment API. The API hangs. The pipeline times out. Suddenly, the deployment enters a zombie state. The old worker is being phased out, but the new worker hasn't propagated. Users start seeing version mismatches or blank screens. The development team tries to roll back, but again, the API is down. They are frozen in code. Scenario C, the fintech fails secure. For a bank using Cloudflare Access, their Zero Trust product, the impact was different. When the authentication tokens couldn't be renewed, the system did exactly what it was supposed to do. It locked everyone out. Employees couldn't access internal tools. Customer support agents couldn't reach the CRM. The bank was secure. Nobody could hack them, but they also couldn't do any business. This highlights the operational risk of zero-trust architectures that rely on a single global provider for real-time session validation. The remediation, how they fixed it. So, how did Cloudflare dig themselves out of this hole? According to the blog, they couldn't just restart the database. The backlog of pending writes and retries was so massive that bringing the system back online immediately triggered the same lock contention, a classic thundering herd. They had to employ a strategy known as load shedding. 1. API gating. They completely cut off external access to the API. No customers could make changes. This stopped the influx of new write requests. 2. Priority queuing. They prioritized internal traffic required for the database nodes to talk to each other, deprioritizing the logging token requests that were causing the edge failures. 3. Code rollback. They hot-patched the migration script to remove the aggressive locking logic. 4. They brought the regions back online one by one. Asia first, then Europe, then the Americas, to ensure the database could handle the reconnection storms. It took 83 minutes to reach full stability. Lessons for engineers. What can we, as builders, learn from the November 18 outage? 1. Decouple the control plane from the data plane. If your configuration database goes down, your application should not stop working. It should just stop accepting changes. Ensure your application caches its configuration locally and has a long TTL, time to live on those caches. 2. Exponential backoff is non-negotiable. The migration script failed because it retried immediately. All internal services must use exponential backoff with jitter. If a request fails, wait 1 second. Then 2, then 4, then 8. Add a random variant so all servers don't retry at the exact same millisecond. 3. Test zombie mode. Chaos engineering usually focuses on crashing servers, but you should test zombie mode. What happens if the server is up but the config database is unreachable? Does your app crash? Does it default to secure settings? Does it lock users out? You need to know the answer before the outage. 4. Skepticism of global dependencies. If you are building a mission-critical system, ask yourself, if this third-party service vanishes for an hour, do we die? If the answer is yes, you need a backup plan. This might mean a secondary DNS provider or a break glass mechanism to route traffic directly to your origin IPs in an emergency. Summary. To wrap up, the Cloudflare outage of November 18, 2025 was a stark reminder that the internet is held together by software, and software has bugs. It wasn't a hardware failure. It was a complexity failure. A database migration interacted with a security dependency in a way that nobody predicted, causing a global deadlock. While Cloudflare's recovery was relatively swift given the scale of the problem, it serves as a warning. As we push more logic to the edge, we introduce more dependencies on the synchronization between the core and the edge. The edge offers incredible speed, but it requires incredible coordination. And on November 18th, that coordination collapsed. I've linked the full technical postmortem in the description below. I highly recommend reading it. It's dense, but it's one of the best pieces of technical writing on distributed locking you will find this year. If you enjoyed this deep dive into system architecture and failure analysis, please hit that subscribe button. We break down the engineering behind the headlines every single week. Let me know in the comments, were you affected by the outage? Did your failovers work, or were you stuck refreshing the dashboard like the rest of us? Thanks for watching, and I'll see you in the next one.